Hi, I'm going to present NeuralFDR, a method that learns discovery thresholds from hypothesis features. In the traditional setting for multiple hypothesis testing, we have a bunch of hypotheses, each with a p-value. From those p-values, we can calculate a threshold, and we discover hypothesis I if its p-value is smaller than the threshold. In some cases, for each of the hypotheses, we not only have a p-value, but have a set of hypothesis features. These features represent the prior knowledge we know about those hypotheses. In these cases, it is possible to learn some feature-dependent threshold, which may potentially lead to more discoveries. Consider the following example. Suppose we are interested in which genes are related to a disease called rheumatoid arthritis. It is believed that the related genes are close to each other in location in the chromosome. So we have a p-value for each of the gene, and as the hypothesis features, let us consider the chromosome index for each gene. We may observe something like this. In this plot, the x-axis is the chromosome index and the y-axis is the p-value, and each dot represents a hypothesis. As we can see, the p-values for chromosome 4 are systematically smaller. This means that most related genes are in chromosome 4. The traditional method neglects this structure by assigning the same threshold for all the p-values. And NeuralFDR, on the other hand, allocates more FDR budgets for the hypothesis in chromosome 4. And by doing this, we can gain more power. The NeuralFDR algorithm proceeds as follows. As input, we take a list of p-values, each with a hypothesis feature. We train a neural network to learn the feature-dependent threshold. And specifically, this is done by maximizing the total number of discoveries, subject to the constraint that the estimated false discovery proportion is smaller than alpha. And finally, we apply the learned threshold on the hypothesis data. For the false positive control, we use cross-validation. Specifically, we split the hypothesis into 3 parts, the first for threshold training, the second for cross-validation, and the third for testing. This leads to a high probability false discovery proportion control theoretical guarantee. As one of the empirical examples, we tested NeuralFDR on the GTEx data. For this data, each hypothesis is testing the correlation between one SNP and one gene. And as hypothesis features, we consider the distance between the gene and SNP and read count. Under the FDR level of 10%, BH can discover 30K hypotheses, and NeuralFDR is able to make 7K more discoveries. And this is done by learning a threshold that is highly dependent on the features. For more details, check out our poster number 124, Tuesday, December 5th.